Hi, Mr. Richards here. Today's lesson is on solving compound inequalities. What you'll learn how to do is solve compound inequalities containing the word and graph the solution set, and solve compound inequalities containing the word or and graph their solution set. Let's start off by figuring out what a compound inequality actually is. Well, by definition, a compound inequality is two or more inequalities that are connected by the words and or. Now, a compound inequality containing and. This is only true if both inequalities are true. So if we take a look at two sample inequalities such as x is greater than or equal to 4 and x is less than 7, well, if and is our statement, what you can do is graph both of these inequalities, and we'll just do a quick graphs here, where we have 3, 4, 5, 6, 7, 8. And if we want to graph our x is greater than or equal to 4 first, that's going to be closed circle at 4, where everything's bigger. Then if we again have our 3, 4, 5, 6, 7, 8, and our x is less than 7, well, that's going to be an open circle at 7 that we're shading towards the numbers that are smaller. Now, when it comes time to combine these, what we're going to look at, and again, we'll have our 3, 4, 5, 6, 7, 8. What we'll do is say, okay, picture a dotted line here. This is true when both graphs are true. So we will have a closed circle at 4, an open circle at 7, and we're shading in between. So this basically is the statement 4 less than or equal to x less than 7. And this can be read x is greater than or equal to 4, and you can see that x is greater than or equal to 4 and less than 7. Or we could say x is between 4 and 7, including 4, since we have the or equal to. Let's look at an actual example of this. Solve each compound inequality, then graph the solution set. Well, our first step here is going to be to solve and rewrite these. So we're going to have 7 is less than z plus 2, and then we'll have and z plus 2 is less than or equal to 11. Now let's solve these inequalities. Well, subtract the 2 from both sides, and we have 5 is less than z. And if you subtract the 2 from both sides of the other inequality, we're left with z is less than or equal to 9. So our solution set can be written as z when 5 is less than z, and z is less than or equal to 9. Now, when I go to graph this, we'll draw our 3 number lines here. And we need in between 5 and 9, so we'll go 4, 5, 6, 7, 8, 9, 10. And I'll do that in all of these here. And again, the closer you can line these up, I mean, if you could do it on graph paper, or you could just try to keep them as close as possible. Now let's graph our first inequality. Z is greater than 5. Well, open circle at 5. And then test. Is 5 less than 4? No. Is 5 less than 6? That's true. So it's true for all the numbers off to the right here. What about the next one? Z is less than or equal to 9. Well, close circle at 9. 8 is less than or equal to 9, so we'll shade it in that direction. And now, when we look for the union, I'm sorry, the intersection, not union, intersection, we're going to be in between here. So we'll have an open circle at 5, a closed circle at 9, and we're shading in between. So that is the intersection of the graphs. Now another type of compound inequality contains the word or. A compound inequality containing or is true if at least one of the inequalities is true. So we need at least one of the inequalities being true. And this is not the intersection, this is called the union of the graphs of two inequalities. So if we're given something such as x is greater than 3, or x is less than or equal to 1, when we draw these graphs, I have 0, 1, 2, 3, 4 on all of these graphs. 0, 1, 2, 3, 4. 0, 1, well that's bad, 2, 3, 4. X is greater than 3, open circle at 3 going to the right. Less than or equal to 1, closed circle at 1 going back to where it's less than. When I look to draw the union, this, in fact, using the word or, is going to be x is less than or equal to 1 or x is greater than 3. So we actually draw both graphs. We have x is less than or equal to 1 or x is greater than 3. You have both. It's not the intersection, it's both. So a ski resort has several types of hotel rooms and cabins. The hotel rooms cost at most $89 per night, and the cabins cost at least $100 per night. Write and graph a compound inequality that describes the amount a guest would pay per night at the resort. Well, if we're looking at most $89 per night, that would be, well, n is less than or equal to 89, because if you think of at most, could it be $89? Yes. Could it be $88? Well, yes, that's true. 87, yes. It's everything smaller than 89, but including 89. 90 is more than 89. It's not at most 89. 89 is kind of the limit there, so 89 or less. Now, the cabins cost at least $109 per night. Well, is 108 at least 109? No. Is 110 at least 109? Yeah. So for that one, it would be n is greater than or equal to 109. So when we go to write the solution set for this one, we would have, okay, use our brace, n with our bar, n is going to be less than or equal to 89, or n is going to be greater than or equal to 109, and we'll close the brace, but let's define our variable as well, where n is the amount a guest pays per night. And when we go to graph this, we don't actually need to do our 3 number lines here. Let's just make a point at 89. Make a point at 109, and you can be as detailed with this graph as you'd like. But I'll just keep it at that. And we'll have a closed circle at 89, and less than or equal to will go back this direction. And greater than or equal to 109, well, we're looking at the numbers that are bigger than 109 or equal to, so we'll shade the circle, and that is our graph. Now as we look at our last example, solve each compound inequality, then graph the solution set. Let's go ahead and write these separately. We have 4k minus 7 is less than or equal to 25. And then we have or 12 minus 9k is greater than or equal to 30. Let's solve each inequality independently. Let's add 7 to both sides. We're left with 4k is less than or equal to 32. Divide by 4, divide by 4, and k is less than or equal to 8 is an option. And in our next inequality, if we subtract 12 from both sides, you're left with negative 9k is greater than or equal to 18. Then divide by negative 9 on both sides. And k is, well, we're dividing by a negative on both sides here, so make sure you change that and reverse the sign to less than or equal to negative 2. Well, let's go ahead and graph these real quick. I'm going to draw ourselves 3 number lines. And we're going to stretch these from negative 3, negative 2, negative 1, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can do that 2 more times. And again, as you do these freehand, they may line up perfectly, they may not. Just try your best. Graph paper may be ideal as you're graphing these if you want them to be absolutely perfect, but here we are. K is less than or equal to 8. Well, close circle at 8. 7 is less than or equal to 8, so we're shading it this side. And then we have k is less than or equal to negative 2. Well, close circle at negative 2. Negative 3 is less than or equal to negative 2, so we're shading it this direction as well. And when we go to look for the union, we have our dotted line here, our dotted line there, and where we're including both here. So both are going to the less than side. And in fact, the graph of k is less than or equal to 8 includes the k is less than or equal to negative 2. And so we could actually just draw our graph and include all these numbers because this part is already included with the blue one. So our solution here for k is, well, k is less than or equal to 8. Since k being less than or equal to 8 already includes the k is less than or equal to -2. That's it for this lesson. Good luck.